Hi everybody, welcome to CITA seminar. It's my pleasure to introduce Eugene Vasiliev from the University of Surrey. He got his PhD in 2007 at the Milky Physical Institute in Moscow, and where he was working on dynamics of dark matter in galactic centers. He then continued there to work as a researcher for a while and moved to the Rochester Institute of Technology in 2012. Then he continued with positions in Oxford, Cambridge, and is now an Ernest Rutherford Fellow in Surrey. He is going to tell us about the interactions between the LMC and the Milky Way, and it's my pleasure to listen to your talk.
It's my pleasure to be here. That's my second time in Toronto. And yes, very beautiful city, and just like clouds and stuff. Okay, so talk about the clouds. Talk about the Magellanic Cloud, the Magellanic Cloud specifically, and how much trouble it causes to us galactic analysis in various ways, troubles and also opportunities. So I should say that I started my life as a theorist, and it all changed when I saw this picture that was on the day of the guy they introduced to, and it shows, see, that's some sort of arrows, fingerprint, it's zooming in on the region of the LMC, showing how stars move around the central bar in the LMC. And since I was doing research on galactic bars at the time, I thought, oh, why don't I go and plot it? And it's easier said than done, of course. So I learned how to deal with the data, with models. I'm still not there. I'm dealing with LMC as a bar guide. That's still on my plan. So at least that's the picture that inspired me to go towards the observation side as well. And today I'm not going to talk about the internal processes in the LMC, but rather about this interaction with the Milky Way system in general. So let me introduce the participants of this story today. They probably know some of them quite well. The Milky Way is a typical standard spiral galaxy, Milky Way-sized spiral galaxy. And LMC, by all measure, is a much smaller object. So we know that the stellar mass is at least 10 times, maybe 12, 20 times smaller than the Milky Way's mass. The total mass that I'm going to talk about in detail is also between 5 and 10 times smaller than the mass of the Milky Way, and by all other properties, it's also a smaller number. So why does it cause so much trouble? Compare the two sides, kind of incommensurable. But indeed, that's a perturbation, but it's not a small perturbation. By the way, this picture here is from the artist Ronald Morisot. You've seen the Toronto Art Gallery, one of the representations artists, one of many interesting artists here. And really like this place. Yes, a lot of nice paintings. We'll see some of them later in the talk. So, let me start by introducing the context, historical context of the research into Magellanic system. Of course, US galaxies have since ancient times, since centuries ago, and for a long while it was assumed that the Magellanic Clouds are satellites of the Milky Way, and moreover, that they have been orbiting it for many orbital periods for the entire whole time. So the in absence of measurements other than just the line of sight velocity, it was assumed that the orbit of the LMC is something like maybe 1 billion years old. We now know that that picture is not correct, and we know it because of first measurements of three-dimensional velocity of the LMC coming from the Hubble Space Telescope 20 years ago. And with this measurement, it turned out that it actually had very high tangential velocity. So if you compute the orbit of the LMC back in time, it turns out to be not the trajectory that comes back, but the trajectory that goes from infinity and just passes near its pericenter very, very recently, something like 50 to 100 years ago. So that's the picture that is the cornerstone of modern knowledge of the LMC-Milky Way interaction, that LMC comes into the Milky Way system from far away and interacts with it. Also, these early studies assumed the mass of the LMC that was much, much smaller than we think it is today. And we'll see later why that's important, how interesting. Another thing about the LMC and Magellanic system in general is that there are not only just two galaxies, but there is also a very prominent gas structure, a Magellanic gas stream that crosses half of the sky, the theoretical observations, and the models indicate that this stream is probably produced by the interaction between the two clouds. So it's the gas stripped from the SMC by the tidal field of the LMC, vice versa, pulled out of the LMC by the SMC, and both clouds fell to the Milky Way, and that's how it's stretched across the whole spectrum. But I'm not an expert, I'm just saying that there is such a thing as a pipeline gas stream. It's not observational fact that we have to contend when doing dynamical modeling. There is some sort of gas there. In addition to that, there are also a lot of satellite galaxies. And SMC itself is widely believed to be satellite of LMC, but for a long time it was the only known satellite. And only in the last 10-15 years, with the advent of very deep electric surveys in the southern hemisphere, it was found that there are a bunch of ultra-faint galaxies that seem to be in the vicinity of the LMC and seem to be orbiting it as the proportions of the galaxies became available. After that year or two, we will have computed orbits of these galaxies back in time and found that they stay in the vicinity of the LMC. So there are micrometer satellites of the LMC, but they are much, much smaller than the SMC itself. And the SMC is also heavily tidally perturbed by this stream, and currently is at least 10, probably 100 times smaller than the LMC itself. I will return to the question of the satellites towards their installment. And in the remaining minutes, I will discuss the effect of the LMC on the Milky Way system in various aspects. And I'll start with the effect of it on the tidal streams. So this morning, actually, you have seen this picture already, the field of streams. It's the very iconic picture from going back to the first release of SDSS. And it's showing that actually the sky around us is permeated by many structures. We have very deep things in the tidal stream, we have a bunch of other things crisscrossing this picture. And the streams formed by tidal streams of satellite galaxies or global clusters. I can illustrate how that happens by this small movie. So let's say this is the host galaxy, this is a satellite galaxy or global cluster in this case. If I draw the contours of effective potential, there are two Lagrange points, like this was our sun system, the moon is here somewhere, and Lagrange points is where the gravity of the central object exceeds the gravity of the satellite. So anything that goes through the Lagrange points gets lost, and forms this kind of tidal stream. And these streams are very useful because they trace more or less the orbit of the perimeter, so you can use them as a probe for gravitational potential and for many other things. So this is a theoretical illustration, and as you can see here, we have many of them observed. Right now, there are probably about 100, or more than 100 streams. This is the updated population here. Many of them were discovered against things to Gaia, but many of them were also discovered to the first. How are streams interesting for the LMC interaction? Because it turns out that some of them actually are perturbed by the LMC in a considerable way. And as I said, the streams normally follow the trajectory of the progenitor, and therefore you would expect that the velocities of stars in the stream would be aligned with the same trajectory as the stream itself. And that's mostly the case, but not always. So here is an example of a stream called Orphan-Chenab. It has a dual name because it was discovered as two separate stretches of streams with the northern and southern hemisphere. And an orphan is because it has no visible progenitor. Chenab is the name of the river, India, I believe. And I would say that this community is actually quite imaginative in naming the objects. It's not just numbers, but they have various names from all world cultures. Anyway, so this stream actually is one of the streams that display significantly the motion of the stars, the velocity vectors of stars, and the streams by themselves. So there are many maps here showing that the stream is also like straight lines, and various bends and twists. And a study led by Venezuela back in Eugene, also with participation of Lee, here and plays a very important role in this stream community. Illustrates the following thing. So here is the estimation of the formation of this stream progenitor here, and the red lines are the observed track of the stream and the velocity vectors of the stream. And as you can see right now, shortly, it's orbiting the Milky Way, and at some point the LMC comes from the Atlantic Sea and passes through quite near to the stream. And you can see that it affects the southern part of the stream quite a lot. So it's became offset from the original orbital track, and also its velocity were so it acted towards LMC, so now we're going towards LMC, and the stream track is this way, so there is a bit of misalignment between the losses and the stream track. And this misalignment cannot be caused by static Milky. So by measuring this misalignment here, so these are measurements, in addition to the model, we can infer something about the properties of this interaction, how close it was, what was the mass of the perturber, in this case the LMC. And this is not the only stream that displays this misalignment. This stream has been studied in much more detail using this type survey, 15 days of mean. And the more recently, Surrey also was able not to measure, not only measure the overall design, but trying to map out the misalignment and the properties of the stream as a function of the closest distance to the LMC, because you could imagine that the strength of the perturbation depends on the mass that LMC has within the radius of the closest approach to the given part of the stream. If the stream is very long, part here might be coming to the 10 kilobars, part here might be coming to the 50 kiloparsec. By measuring the strength of the perturbation and at these different places, they were able to map out the enclosed mass of the LMC as a function of distance from it. So it's a very delicate probe of structure of this galaxy. That's possible because the streams are generally very fragile, very thin, fundamentally cold objects. So any perturbations that we see in them will be readily quantified and used with very sensitive dynamic probes. There are a bunch of other streams in the southern hemisphere that display similar level of slam, and for them there was no such detailed modeling, but just an overall estimate of the relative mass that by Norship causes. And they all converge more or less in the same range. So this is the mass, something like between 1 and 2 times 10 to the 11 solar masses. That's compared to the Milky Way's mass of 10 to 12 solar masses. So that's one indication that LMC is quite massive. There is also a stream that you already seen in one of the previous pictures. That's the most massive and most prominent stream in the sky in the Milky Way. It's called Sagittarius stream, named after the galaxy that is its progenitor. This galaxy itself was discovered only 30 years ago. So it's sitting more or less close to the galactic plane and behind the galactic center, so it's hiding behind the galactic bulge, which is something like something kiloparsec. And this galaxy will start, and then shortly the stream crossing full sky was discovered. The geometry of this the stream is such that it is basically perpendicular to the galactic plane. So the display is here. The Sagittarius stream is in this plane, and the LMC that is here is also its trajectory is roughly perpendicular to the galactic plane, but they are also orthogonal to each other. So while the Sagittarius goes this way, the LMC comes from here. And at some point in the southern hemisphere, they also come to close vicinity to each other. And therefore, we could expect that LMC causes some perturbations on the Sagittarius stream as well. This stream is so massive that whenever you look at the outer halo, basically, unless you look at a completely different direction, you find something with Sagittarius. It's the most prominent structure in the galaxy, and of course, it was mapped in exquisite detail by many people, especially after Geiger. And several years ago, I was also became interested in following this stream and set about to create a stream model. So having a simulation of a disrupted galaxy that matches the large amount of data that we have currently. This amount of data is basically a six-dimensional map of the whole stream. There are many panels here, but let me say that these 4 panels show different kinematic properties, like the proportion in one direction, in the other direction, distance, and the line side velocity, as a function of the coordinate of the stream. This is the spectrum view of the galaxy. So this is the size here, the center is here. So I should be showing it here so that you want to find it. So this is the progenitor Sagittarius galaxy sitting below the galactic plane and behind the galactic center. And the coordinates here go like this is the positive coordinate in the leading arm of the stream, and the trailing arm is the negative lambda. So all the quantities here are plotted as a function of lambda, and the stream spans more than 360 degrees in the sky. And one thing that is also quite prominent in this stream is shown here, again, the stream track and the directions of the proportion. So there is a similar kind of misalignment between these two things, which can also be quantified in this lower panel here. This is the one of these curves is the derivative of the stream track, and the other is the direction of the proper motion. So if there was alignment, they would match each other. But you see in the data that there is some. But you also notice perhaps that most of this misalignment is actually happening in the leading part of the stream. Here. That's quite interesting. So how about modeling this stream? Basically, you launch an embodied simulation of the galaxy on an orbit around the Milky Way, try to match the properties of the stream in all 6 space dimensions by varying the mass of the progenitor, mass of the Milky Way, the gravitational potential of the Milky Way, initial conditions, all this stuff. And yes, yeah.
So I remember a while back, people were using Sagittarius stream to argue that the halo is triaxial.
Yes.
Does that mean it's no longer triaxial, given this hypothesis?
Well, I haven't said it yet, but in fact, we still need it to be at least triaxial, if not more complicated. So, we're doing
And the evidence?
the evidence is that you cannot fit the stream track if you put a spherical halo or even somewhat flattened halo. It's not possible to match the stream track on sky while simultaneously matching the chromometries of light side velocities. So in doing this model, which I'm showing here, this is the data, and I try to fit these solid black lines in each panel. And this model has a very flexible nuclear potential, has actually tracks tightly with the axis ratio that changes to the radius and some twist. It was a very flexible model, like 10 free factors for the potential or something of that order. And even then, I could not match all the properties of the stream, and I highlight the areas where the match is not good. One is the distance to the apocenter of the leading arm, so it's in models it's further away than the data ones. And another aspect is this absence of misalignment, because this model has a static nuclear potential, so the stars lost from the stream still move on the same direction as the stream itself. So this model is good but not perfect fit. This model does not have LMC. If I add the LMC in this model, and make the LMC orbit the Milky Way, and then Sagittarius move in this combined gravitational field of both galaxies, this is what I get instead. So in this case, I'm able to fit both properties much better. And the mass of the LMC that I included here is about the same order of magnitude as inferred from other streams. Of the fact that I extend to the level small masses. And this one still has a triaxial field, by the way. So I was not able to get rid of it.
But the triaxial evidence was because the plane shifted, right?
Yes, and part of this shift is caused by the LMC, but it's not enough to explain the whole thing. I believe that the negative part here was that LMC perturbs the Milky Way, certainly not only moving it away, but also deforming it. And that's the thing that is not fully captured in these kind of simulations. So this remaining triaxiality might be attributed to it, but it might be a intrinsic property, and there is no reason why I moved the accident in the first place. There are reasons to believe that the tracks are even more complicated. But in any case, that's the thing that comes out of this modeling, that that's a complicated halo, and you still need an LMC to perturb it even more. So, as I said, most of the perturbation occurs in the leading arm of the stream. If you remember the previous plot where the Sagittarius was crossing the Milky Way from below, LMC was crossing the Milky Way from below, the closest approach is in the trailing part. But most of the deviation happens in the leading arm of the stream. So it's not an immediate perturbation of the LMC that causes this, must be something else then. What is that? Well, it turns out that, let's skip this slide. Okay, no, I don't skip this slide, I'll just mention something before I go to the more details. The gravitational field of a galaxy like LMC moving through the bigger galaxy can actually cause perturbations at different levels. One of the most well-known ones is the dynamic friction. Any object that moves through a sea of background stars deflects their trajectory, so this object is moving here. Actually, a movie of this as well, illustrated. So here, an object that moves here, could be imagined, deflects the trajectories of passing stars, so that they form a sort of overdensity. Maybe in the top panel, barely means that there is a bit of overdensity of things here compared to the rest part of the model. So this overdensity then causes the gravitational pull and creates the friction force of the object. So this kind of dynamical friction induced wake. The standard thing we expect to find this kind of wake behind the LMC on its path forward. And there were some indications that we see. This wake would exist in both dark matter and stars, but only traces in stars, of course. But it was detected as a bias overdensity. But that's not the only thing. That's the most well-known one, but not the only thing that a massive star can cause. Because overall, there is a deformation of the Milky Way as a whole, not just a local deformation as a wave, but more global deformation. And to illustrate it, let me play you another movie where this is a simulation of Milky Way on the red, on the green, and these two galaxies are orbiting. It's not that LMC orbits, it's that both galaxies are orbiting the concept of mass or something. Right? So initially, the Milky Way is moving towards LMC, LMC is moving towards the Milky Way. As the simulation progresses, the LMC comes from the southern hemisphere, and arrows here indicate the trajectories of individual stars, contributing stars, bunches of these simulations. And the contours show the intensity. So initially, the galaxy was close to spherical, and as you can see, once I put in the LMC, these contours kind of bulge out here. So basically, there is an overdensity around the LMC, and the velocities are also pointing here. Stars moving, they create this wave behind the LMC. This is the classical dynamical picture you see. But also, you see that the whole thing itself is also moving, and it's moving down, because that's where the LMC was, here is mass. So the whole Milky Way is moving down. Good. That is not quite the end of the story, because it moves down here, showing the person. The inner part of the Milky Way moves down. The outer part, you see the velocity vectors here don't go in the same direction. Because the Milky Way itself is deforming. Yeah, it's not a rigid body. And this is what is shown in this body. So the axes are flipped, but the idea is the same. The inner part of the Milky Way moves down. The outer part of the Milky Way does not move down. We, as observers, are sitting roughly at this distance, 8 kiloparsec compared to 50 kiloparsec distance to the LMC. So we are sitting in this region, which all moves down here. Our coordinate system, therefore, is not an inertial coordinate system, but it's the one that moves down, was accelerated. If we transform to this coordinate system, everything else will be moving down. So that's how the whole deformation comes about. In the coordinate system associated with the inner part of the Milky Way, the outer halo mostly moves up towards the northern hemisphere. And that's what creates the density and the line perturbations. In the density, you can see that in the contours, the solid contours are. Yeah, the dashed contours are the initial density, and the solid contours are the perturbed currents, current density. And you can imagine that the star that was finding itself before the LMC came in was sitting in the northern hemisphere, let's say 100 kiloparsec from the center of the Milky Way. Because the center of the Milky Way has shifted down by something like 10 kiloparsec or 20, this star has not shifted yet. So it's finding itself now at 120 kiloparsec, but the density of stars there is still the same as it was before. So now there is an overdensity north because these stars sit there, the Milky Way has moved down, so there is a hard overdensity north, and corresponding underdensity to the south. And likewise, the stars in the north, they move up. With respect to the Milky Way stars, in the southern part, they move down, stars sideways, they move sideways. So this is what we call the collective response, or it's basically a dipole perturbation of the outer halo. The upper part, or here it's not exactly upper, it's slightly shifted, but the idea is that this perturbation is created by the deformation of the Milky Way as a whole. And what I'm showing here is that the amount of false perturbations are quite considerable, tens of 1%. So this has been shown by many people, many different independent simulations, and also using more like kinetic theory calculations, they all point towards the same kind of effect. There is a local dynamic confusion-induced wave and a global deformation of the wave. And what kind of observation predictions would it lead to? Here is the illustration how this guy would look like if you were to look at the density and the velocity components, the time side velocity and two tangential velocity. So basically, on the top two panels are particularly interesting because in the density, this is the inner part of the galaxy up to 60 kiloparsec, and this is the other 60 kiloparsec. So in both the density and in the line side velocity, we see this big dipole perturbation, north-south asymmetry. The northern part is overdense because the stars are now at larger distances than they were originally, and they also move up north. So in the north there is a positive line side velocity, in the south there is a negative line side velocity. So these are all predictions from these kind of models. They depend to some extent on the adoptive potential of the Milky Way, adoptive mass of the LMC, but qualitatively this is all the same. And interestingly enough, this is one of relatively few cases in recent statistical studies of the Milky Way that predictions were made before the data came in. Most of the time we had to deal with something unexpected coming up with data, but this was a theoretical prediction based on the stream, and then we also went back after the layer to came in and checked the velocities and the densities of stars, and it turns out that yes, indeed there is this north-south asymmetry in the outer part of the Milky Way, in the tracers like stars in the Milky Way tail or satellite galaxies. And the lower panel here shows the observed kinematic properties, the mean north-south velocity asymmetry, and the top panel shows the density asymmetry. Density actually is much more difficult to get right, because it depends on so many factors like the coverage of the survey. So we're able to make some correction for it and observe qualitatively similar predictions to the qualitatively similar effects to the predictions of the models. So this is the global effect of the Milky Way, and that's the effect that causes the deflection of the secondary stream in the north, because basically the north part of the stream was similarly affected as the north part of the halo. That is to say, it did not move as much as the inner part, so it found itself shifted with respect to the inner part of the Milky Way. So it's not the local perturbation of the LMC, but it's the global perturbation that caused this misalignment in Sagittarius stream. Okay, so this amount of perturbations is considerable, tens of kilometers per second in velocity. That makes some 10% of the velocity dispersion in here, which is over 100 kilometers per second. So any measurements of the Milky Way gravitational potential would be significantly affected by this. So the main study from the circle in 2019 showing that if you neglect the perturbations, you would get an overestimate of the Milky Way's mass, enclosed mass assumption values, and the overestimate goes larger at larger distances. I think qualitatively that could be understood as basically extra velocity in the outer part of the halo, and if added to the velocity dispersion, you get an overall higher kinetic energy. And therefore, it should be balanced by larger potential energy, so you don't have to make the LMC more mass, but the Milky Way more mass. Just not quite correct. As I said, the measurements of the measurements of the Milky Way potential can be roughly split into two big groups. One is based on the star stream, fitting the stream track, including all these perturbations that we have seen already. And the other classical modeling methods, they are all based on assuming dynamic equilibrium. So that's where things go wrong, because we are not in equilibrium anymore. And regardless of the specific methods that I listed here, there will be biases. And the question is what to do with that. But it turns out that they can actually compensate for it in a rather straightforward and elegant way. That was the project that I done with the summer students several years ago, the experiments. And the assumption here is the following. If the LMC is causing these perturbations in just very recent times, what if we try to undo them and assume that before the LMC came in, so like 2-3 years ago, the Milky Way was much closer to the equilibrium than it is now. So we could do the following thing. For any, we try to infer Milky Way potential. For any assumed choice of Milky Way potential and the LMC mass, we could try to unwind back the orbit of the LMC and Milky Way, accounting for all these perturbations, these reflex motion of the Milky Way created by the LMC. So we have a time-dependent potential of the Milky Way, and in this time-dependent potential, we can then integrate the orbits of our tracers in the field back in time for a couple of years ago, and then at this time when the LMC is far away, we assume that tracers work in equilibrium. So we are kind of doing inverse forward modeling in some sense, but it's a forward modeling, but it's iterating back in time. And then at this time, the tracers were in equilibrium, so we can apply these classical modeling methods. This case, we are choosing the distribution function-based method. I'm going into the details, but basically it's the idea that things were in equilibrium, and we could try to infer the gradation potential that makes the best fit to the observed data set. So in this case, we are using the data set of the 6 basic coordinates, and these come from global clusters. Most of them are in the inner part of the Milky Way, but some of them are further out, and satellite galaxies. And these are much further out, so they're more strongly perturbed by the LMC. And in this exercise, therefore, we will infer the potential of the Milky Way, the mass of the LMC, and also compute how the properties of its tracer orbits change in time as the effect of the LMC as the effect of the LMC comes. So here's a very confusing problem. We won't go through some of this fast. This shows the orbits, the past orbits of thousands or so of satellite galaxies of the Milky Way in two different situations. One is where we do not have LMC, we get the effect of the LMC, and this is in blue, and red is with LMC, yes. And the green output of it. What is shown here in each panel is for each galaxy we have the past trajectory shown as just a data-centric distance as a function of time. Present day is here, and this is integrating into the past. And what I want to draw attention here is that the red curves and the green curves, they are all cycling over the uncertainties in the measurements and also the uncertainties of the nuclear potential, which is inferred in this study. But some of them look pretty similar, so there is no significant effect in this case. But in some cases, like Draco, Ornax, some of the classical satellites of the Milky Way, Leo 1 and so on, they actually have very different orbits in the past, depending on whether you account or not account for the LMC perturbation. And this is also more clearly seen in these green curves, which are showing the time evolution of the orbital energy. So if there is no perturbation, the energy will be conserved. If there is perturbation from the LMC, then energy might go up or down, and that depends on where the galaxy is with respect to the nuclear galaxy system. So for a galaxy like Spotter, its initial orbit energy was higher, it was less tightly bound until very recently, and then when LMC came in, it dropped back to the current energy. So the orbit without LMC would have been more tightly bound than the current one. The one is more realistic. For this galaxy, it's the opposite. Its orbital energy went up, and this galaxy, Leo 1, is actually the one that caused a lot of troubles in the past, because it's the galaxy that is now moving away from the Milky Way. It's just like a Milky Way satellite, but it's moving with such a high velocity that in order to keep it bound, you need to put a Milky Way mass that is very massive. So this was used as a galaxy that would kind of set a lower limit of the Milky Way mass, we assume that it is bound. As to be seen here, actually, it was on much lower energy orbit until very recently, just how it's pushed up right actually. So accounting for the LMC perturbation actually brings back the Milky Way mass down. And some galaxies like SSC have very different orbits, because they are basically satellites of the LMC. So if you neglect the effect of the LMC, it would be completely different orbit. Right. So going back to the question of the measurements of the Milky Way mass potential, well, mass profile potential, there have been many studies over the last years, especially since 1902. And here's a compilation from the recent review that we published with James Collins on the Milky Way dynamics. And these all come from different studies, different methods, tracers, but the three shaded regions indicate the three studies that accounted for the LMC in their analysis. Two of them was based on streams. This orphan stream that I talked about first, and Sagittarius stream that I talked about next, and then the most recent one is this latest one. The red one is the study that I just talked about, looking at the dynamics of galactic satellites. They all kind of like this degree more or less. And the neglecting the LMC would be shifting this slightly up, although on this scale here it might not be so noticeable, because the uncertainty of the measurement of the nuclear mass is still considerable, let's say 10-20%, 20% at least. And the LMC mass, by the way, also coming from different studies, they all converge more or less the same mass range. I said it's between 1 and 2 times 10 to 11 solid masses. Now, much time do I have? 10 minutes?
10 minutes, yeah.
Okay. Yeah. One thing that I wanted to mention is that these are all tracers in the outer part of the Milky Way, and studies based on streams or satellites and so on, beyond, let's say, 20 kilohertz or so. Now, people have also used tracers within the Milky Way disk, and using these equations to infer the Milky Way's mass profile in the inner part. And interestingly enough, they almost agree with these outer tracers. So, having a few studies in the past that indicate that the Milky Way circular velocity has a very sharp drop beyond 20 kilohertz or so. And the dashed line in this plot There is no dash line here, but the dash line, if I were to plot it here, it would basically go through this all measurements. It would be a fiducial Milky Way potential, something realistic. There is no way to fit the same kinematics in the outer part of the Milky Way and still fit the kinematics in the outer disk. So all of them at least must be somehow wrong or biased. There are good reasons to believe that these amendments might be biased by neglecting or not fully accounting for the LMC perturbation, because the outer part of the disk also is affected by the LMC. So there have been recent studies that show that LMC might be partially responsible, at least, for this disagreement between the mass profile of the Milky Way from disk kinematics and from field kinematics. But that's a whole topic. All right. So in the last 10 minutes or so, I'll touch upon the final part of my talk, that is this past orbit of the LMC and the kinematics of the satellite. And the thing is, so what I described so here looks like a brilliant picture, we know everything, but that's actually not quite the case, because the measurements of the LMC's past orbit depend very strongly on the measurement, sorry, the past orbit of the LMC depends very strongly on both the measured velocity at present time and on the past and on the mass of the Milky Way, or the radiation potential of the Milky Way. So here is a compilation of several recent studies. They, apart from this data point, which is the first HST-based proper motion measurement that I talked about at the beginning, most recent studies converge more or less in the same region. We still don't agree with the error bars. They're roughly in the same region. But even these relatively small differences here, they translate to very large differences in the past orbit. So all of them would end up with an LMC 50 kiloparsec right now. But if you integrate back orbits starting from these different velocity values, you will get orbits that are kind of bouncing back or orbits that fly away. And this much uncertainty here is caused by the fact that the LMC is now just marginally bound. Its total energy is close to zero. So even small changes in the kinetic energy cause actually quite large changes in the total energy. And likewise, there is a strong sensitivity to the atomic Milky Way potential. If you change it by just 10% up or down, you can make an orbit that very strongly unbound, an orbit that actually has a cloud center sometime in the past and another clear center in the past. So these plots I prepared for the review of the Milky Way interaction I wrote 2 years ago. They're basically covering all the topics that I talked about. And I was reiterating this common view that the LMC is the first approach to Milky Way just now. Then I looked at this context of the fact. This doesn't look like the first approach for sure. What if I play a devil's advocate and try to construct models that actually have a second approach in the LMC? So after a few weeks of hard work, I came up with a series of models where indeed the LMC has experienced yet another recent approach in the past and now comes back to the second time. So this second passage scenario is, I should make it clear, it's not the dominant point of view. Serious doubt about it myself, but it's a plausible scenario given what we know about the Milky Way and the LMC properties at the moment. So if that happens, if the LMC comes back in the past, you see that there is still quite a large variety of possible orbits. Here, the Milky Way mass was only varied by 10%, and the LMC mass was also varied in some ways, and that changes the orbits quite considerably. But if it happened that it had another percent passage in the past, it would be quite far away, something like 100 kiloparsec per center distance, and it would have happened many years ago. And all the perturbations that I talked about, streams, air kinematics, they all look exactly the same in the first and second passage scenarios. That was very disappointing. I could not find almost any way of tracing whether probing observation, whether the first or second passage scenario is true.
Except star formation.
Star formation is a good one, yes. In the LMC, we have some indication about star formation history. It's relatively flat in the past, although there are some hints that it might be having some bumps in the few years ago. The thing is that it's more likely to be affected by the SMC interacting with the LMC rather than LMC or the Milky Way. Because back in the even if this scenario is true, the past 100 kiloparsec from the Milky Way center will be still protected by a very large envelope. So I don't think it will have a significant effect on the star formation history or the LMC amount. But that has this type of effect. Here that has not been explored in detail. But there was one thing that actually made the difference in the first and second passage scenario, and these are the kinematics of the LMC satellites. So I'll skip this part and I'll go to the question of satellites. The LMC satellites, or things that could be possibly associated with LMC, in these simulations I could actually make a very quantitative assessment of the probability that the new galaxy is currently a satellite of the LMC or has been a satellite in the past. And here are some examples. So there are like 2,000 galaxies listed here with the probabilities of being current satellites, that is blue, or former satellites. The larger is the power, the larger is the probability. How that is computed. So here's an example of some possible galaxies like SMC, that is very clearly current LMC satellite. Its galactocentric distance as a function of time stays in close vicinity of the galactocentric distance of the LMC itself, which is shown by the dashed line. So that is to say that it always stays in the vicinity of the LMC. A galaxy like Bruce 2 is one of the occurring galaxies. We don't know much about its proper motion, so there is large uncertainty here, and there are roughly equal chances of it coming from the LMC system. So there is a blue series of lines, and being satellite of the Milky Way, so it was always staying in the vicinity of the Milky Way. So both sets of trajectories are compatible statistically with its present condition model. There are examples like these two, where a galaxy would have come with the LMC system, and on the first passage of the LMC would have been stripped and put to a very different orbit, and now it's orbiting the Milky Way, so it's nowhere close to the LMC anymore, but it still has a trace of coming to the LMC system. And again, quantified for these galaxies, and there are about a dozen or so that would have been associated with LMC in the past, various degrees of certainty, and would have been stripped on the first periscope passage. So let me maybe play you. Before I play a movie. No, I'll play it first. So here is the illustration of it. I guess you can see it here. So this is the LMC, this is the Milky Way system, the blue is the Milky Way, red is the LMC, and there are a few particles here that I picked as possible satellites. Sorry, they're a bit strange, but you'll see that they're orbiting the LMC that comes in. On the first passage, almost all of them got slinched away from the LMC, and they keep orbiting by themselves. Only one that here remains, this is the SMC. And by the time the LMC comes back for the second time, well, these galaxies are all over the place, except SMC. So how do we know that they could be associated with LMC? Because they keep track of their orbital properties. They are still orbiting in the same orbital plane. And this is the last part of my talk, talking about this effect that we know in the Milky Way system, and it's one of the nearby galaxies. Satellites are not distributed uniformly in the sky, and in the Milky Way, many of them are aligned in a certain orbital plane. It's called plane of satellites. Not only that, they also seem to be aligned in the direction of their angular momentum. So this information came in more recently, to Galileo 2 and later, and the direction of angular momentum is also plotted on the sky plane. So this is the sky sphere, but it's not the physical position, it's just the direction of angular momentum. And LMC is positioned so that it sits basically in the center of it, and galaxies that are currently LMC satellites, they also and which are very close, not surprisingly, but the galaxies that are shown in red, these are the former satellites that would have been stripped on the previous passage, but they still retain more or less the same orientation. So this second passage scenario, therefore, naturally explains why some galaxies that are not currently LMC satellites, they still keep orbiting in the same plane. So it's not necessarily explaining why this plane exists in the first place, but it only says that given what you know about the types of these satellites, it might be that yes, some of them would have come with the LMC and were stripped in the previous passage. And if the second passage scenario is not correct, then we'll have to explain it somehow, because there will be no reason why they should see it. So this is the illustration that you see on the poster, and more paintings here. But basically, it's kind of showing the same system here, the Milky Way and LMC debris, and red and blue are galaxies that are currently and formerly associated with LMC, and the stream times. So this scenario still needs to be proven because I mentioned at the very beginning that LMC has significant gas content. This is only left here, so it has to be run with the proper gas dynamics, also accounting for the SMC as a perturber of the LMC system. this is an ongoing research. But for now, I'm good with this and saying that LMCs gives the dynamic troublemaker in the autoparticle Milky Way, creating a lot of perturbations in the halo and the matrix of satellites and other objects. And unfortunately, despite a lot of research, we don't still know its precise properties very well. And the second passage scenario depends mainly on the Milky Way potential. To make Milky Way more massive, shorten the orbital time scale. Therefore, the second passage scenario becomes more realistic. Vice versa, if it could be ruled out from some other arguments that places constraints on the Milky Way potential. But for now, it's possible, but not necessary. In this case, if it was a second passage, then some of the satellite galaxies would be coming from the LMC system. And that means that I'm happy to welcome the LMC back. Thank you.
Other questions in the audience? Yes.
Yeah. We see the misalignment of proper motions in the orphan gymnast because of this like shifting down that we talked about. That should also be injecting some velocity dispersion to part of the stream in the upper arm. Should we be accounting for those when we're trying to measure velocity dispersion in northern hemisphere streams? Because we try and use that to constrain dark matter perturbation, but large, like what do you think the contribution
My
is there?
feeling is that I'm not doing this model myself. I think the velocity dispersion actually is not that much increased because the whole thing is just shifted to a curve instead of being off. It's not like a perturbation from a small halo flying by. That's what people try to use as a constraint for dark matter models. How much heat you get from the environment and small halo. But it's a big thing that shifts the whole part of the stream as a whole.
Okay.
Yeah.
I wasn't sure what you mean that you were maximizing the likelihood of you were reconstructing. You said you were maximizing the likelihood of unperturbed distribution. What do you exactly mean? So you start from some funny dynamic equilibrium, and then you're putting down some perturbed, and then you combine it. And then you say you want to maximize the likelihood.
Yes, and maximizing the likelihood of the unperturbed potential. Yes.
What's that exactly?
Well, in this dynamical modeling method, we try to match the present day positions in most of these trace populations. And I think a combination of distribution function and potential. So you could imagine that, let's say, I can find the distribution function that describes the present day positions and velocities, but if I maximize this likelihood of drawing the tracers from the given population, that places constraints on the potential. So let's say if the Milky Way is 10 times more massive, I would likely find that the same object with much higher velocities. So not only where they are, and fit where they are, they will be much less likely to have these kind of velocities that you currently have if the potential is much more massive.
How do you know your tracers are a fair representation of distribution?
That is a fair question. So that's why I'm not using halo stars here, but I'm using the satellite galaxies and global clusters. You could argue how complete is this sample. It's probably not complete. Most of the incompleteness for global clusters comes from inner part of the galaxies. We still keep discovering new things. For satellites, not here, we still keep discovering things far out in the halo. And as long as these are not, let's say, we estimate how much we would be affected by unseen population satellites beyond, let's say, 200 kilobars, and it's not a significant factor. But it's true that we probably don't know the full sample yet. So that's one potential source of uncertainty here.
You cannot use halo stars.
Halo stars are more, if people use them, they're more difficult because for them we don't know the distances just as well.
Right.
And also the question of completeness is much more acute because the coverage isn't very uniform. Yeah, you could try to assume, but you could try to, there are techniques how to circumvent it to some extent. But
are there chemical signatures for populations that have come off of the LMC into the orbit? And vice versa, if the LMC has stripped any loosely bound Milky Way halos, now have those as current?
Okay. That's a good question. So I talked about the stream, I said it's a gas stream. And the streams that I talked just a couple of slides later were all stellar streams, which is we have a stellar stream from the LMC because it comes around the Milky. We don't have a strong gradient story. There are a couple of stars that find, let's say, a bunch of stars, a handful, maybe 20 or so, in the draining part, and it's a bunch of stars in the leading part of the stream, but compared to what we have for Sagittarius, which was much smaller galaxy. The stream covers the whole sky, and there are like 50,000 stars that we observe. This is nothing. The question why LMC does not produce a stream observers. I think it's because it's just further away from the Milky Way. Even if it orbited for 10 giga years, and the previous very center touch checked that it would not stream stars from the inner part of the galaxy. They're protected by the big magnetic field. So yeah, if the LMC keeps orbiting, which of course it does, in a couple of years from now, you'll see beautiful LMC stream of the whole sky.
More questions? I have a bunch, but I have time. So I think we can take Eugene again for this talk. And there are cookies upstairs for more discussion.